Today we're going to talk about Chapter 11. So the Sun is a star. It's a luminous ball of gas more than 100 times bigger than the Earth. And it kind of looks quiet from our naked eye view, but if we look at it through a telescope, we're going to see a lot of violent activity. Fountains of incandescent gas, twisting magnetic fields. The Sun's core is equally violent, with a furnace of thermonuclear fire converting hydrogen to helium to the tune of energy production equivalent to the detonation of 100 nuclear bombs each second. The force of gravity keeps the Sun in check for now. So with a radius of 100 times and a mass of 300,000 times of the Earth, the Sun has to expend a large amount of energy to withstand its own gravitational desire to collapse. To understand this process requires detailed observations as well as sophisticated calculations involving computer models of the laws of physics. So the Sun's distance from the Earth is 150 million kilometers, or 1 astronomical unit. And it was once measured by triangulation, but now it's done by radar. Once the distance is known, its diameter, which is about 1.4 million kilometers, is found using its angular size. From the Sun's distance and Earth's orbital period, we can use Kepler's modified third law to give us the Sun's mass. And now that we know the mass and radius, the surface gravity of the Sun can be determined. It's about 30 times that of the Earth. So our 180-pound man that we've been talking about would weigh 54,000 pounds on the surface of the Sun. The surface temperature of the Sun is almost 6,000 degrees Kelvin, and it's found from the Sun's color using Wayne's law for a black body object. Now then, if we apply the laws of physics as we understand them, we establish the Sun as gaseous throughout with a core temperature of about 15 million degrees Kelvin. From the amount of solar energy that reaches the Earth, which is 4 times 10 to the 26 watts, this energy must be replenished by fusion processes in the core. Now the Sun has plenty of hydrogen for fusion. Its surface spectra shows the Sun is about 71% hydrogen, 27% helium. Now we can start to look at the Sun. We can start with the center out. The center in the core is where we get all the fusion happening. We'll talk a little bit about that. And then we get a radiative zone of that energy coming out. And we get a convective zone where we get the heat from the inner part of the Sun goes up to the coldness of outer space. We have different things on it we need to talk about, like prominence that's coming out here, or sunspots. We have the chromosphere, which is the Sun's lower atmosphere, and the corona, which is the Sun's outer atmosphere. So the low-density upper layers of the Sun, where any photons created there can escape into space, is called the photosphere. This photosphere is going to be the surface that we see with our eyes. Layers below the photosphere are opaque, and photons created there are absorbed and re-emitted by atoms that are located there. So we can't see inside of the Sun. However, we can do calculations that shows that the Sun's temperature and density both increase as the core is approached. The density is similar to that found of water at sea level on the Earth at the Sun's surface, and 100 times that of water at the core of the Sun. Since the core is hotter than the surface, heat will flow outward from the Sun's center. So near the Sun's center, energy is moved outward by photon radiation, a region surrounding the core known as the radiative zone. Photons created in the Sun's interior do not travel very far before being reabsorbed. Energy created in the Sun's center will actually take about 16 million years to eventually diffuse to the surface. Above the radiative zone, energy is more efficiently transported by the rising and sinking of gas, and this is called the convection zone. And convection manifests itself in the photosphere as granulation, or if I look very carefully here, I see granules of material on the surface of the sun. The darker areas are where the cooler gas is falling back into the sun, and the warmer areas is where warm energy is radiating out. You see all the granules here around the sunspots, which we'll talk about soon. Now, since the sun is all a ball of gas, it kind of seems strange to talk about the atmosphere. But the atmosphere is what is going to be above the photosphere, the visible surface of the sun. It's extremely low-density gases that lie above it. The density of the atmosphere decreases steadily with altitude and eventually merges with the near vacuum of space. Immediately above the photosphere, the temperature of the atmosphere decreases, but at higher altitudes, the temperature actually grows hotter, actually reaching temperatures of several million degrees Kelvin. The reason for the increase in temperature is unknown, but there's speculation at this point that it's the sun's magnetic field that's causing this high temperature. The lower part of the atmosphere is referred to as the chromosphere. The chromosphere appears as a thin red zone around the dark disk if we look at a totally eclipsed sun. The red is caused by the strong red emission line of hydrogen spectra, hydrogen alpha it's called. The chromosphere contains millions of thick columns called spicules, each a jet of hot gas. In this picture you can see here all the spicules of jets of gas shooting off the surface of the sun. Now above that is the corona. The temperature in the corona eventually reaches about 1,000,000 degrees Kelvin. Not much energy though, due to its low density. The corona, which here we can see is visible during a total solar eclipse, can be seen to reach outward over several solar radii. The corona is not uniform, it has streamers and holes in it, and those are dictated by the sun's magnetic field.